So I'm a slide with you. In the last session, we have gone through. In the last session, we have gone through top-down PDA, top-down push-down automata. Now we'll discuss non-deterministic bottom-up push-down automata. Okay, is my voice clear now? Yes, can you hear now? Okay, thank you. So now what we'll do is, to construct a bottom-up non-deterministic PDA, we'll first learn a shift-reduced parsing. We'll understand working of this parsing that is known as a shift-reduced parsing. Shift-reduced parsing begins with the input string. So basically, in top-down parsing, we are going for a leftmost derivation, while in case of shift-reduced parsing, we are dealing with the input string, and that input string will reduce into the starting symbol of the grammar. It uses stack as a data structure because it is a push-down automata, and initial symbol on the stack is Z0. It is Z0. So now let us see that what we are doing in top-down parsing. If we want to derive the string A plus A, and we have the grammar S gives S plus A or S gives A. We have two alternatives for non-terminal S. So if you consider a leftmost derivation, then it is very simple. From starting symbol S, we will derive S plus A. Then the leftmost non-terminal is S, which is shown with a yellow color here. We are getting A plus A. Now when we are dealing with a bottom-up parsing, so we are reducing A plus A into S. So when we are reducing this A plus A into S, in bottom-up parsing, as we are using a stack as a data structure, then the black A, the leftmost A will be pushed on the stack. So it will be at the bottom of the stack. Are you getting this? The leftmost A, right? The leftmost A, we are pushing on the stack first. So it will go to bottom of the stack. Then we have a plus sign and the rightmost A, right? The rightmost A, that will be on the top of the stack. So when we are doing this reduction, right, because we have to reduce A plus A into S, so you can see it is like a mirror image, right? So what it tells that A plus A, so the leftmost A is first reduces to S. The leftmost A first reduces to capital S, and then A plus S, which is in the reverse form of the actual grammar. Because in the stack, what will happen? Our string will be in a reverse order. Our string will be in the reverse order on the stack, as you can see here. Clear? So definitely our grammar rules will be also in the reverse order on the stack. So that's why we are getting A plus S, and that A plus S reduces to S. So that is how we are doing the reduction process. Because we are pushing the string on the stack, your string will be in the reverse form. Your string will be in the reverse form. As it is in the reverse form, we require a grammar rule also in the reverse form on the stack. So you can see the leftmost A reduces to capital S, and then A plus S, which is the reverse of the actual rule, it will reduces to capital S. That is how we are getting the things. So now to understand this, let us have the complete process here. A shift reduce process. We have a Z0 on the stack. Our unread input is A plus A. So first we are pushing A on the stack, the leftmost A. We are pushing the leftmost A on the stack, as you can see here. Now you can see that this leftmost A is at the bottom of the stack, right? It is at the bottom of the stack. So now, as per the reduction, which is from bottom top, you can see at the bottom, we are reducing this A to capital S. We are reducing this A to capital S. Because what we want to do, we want to do the same thing, a leftmost derivation. We want to do the leftmost derivation, but it is in a reverse form, right? We cannot change that. We are doing a leftmost derivation steps, but in a reverse form. So that's why the A is reduces to capital S. A reduces to capital S. So that is what we are applying. We are reducing A to capital S. So when we are reducing A to capital S, we are not consuming any input symbol. We are not consuming any input symbol. Now we are shifting plus. So we'll shift plus on the stacks. We have plus S Z0. We have plus S Z0 on the stack. Now we'll further shift A because we don't have a rule for plus S. So we'll shift A on the stack. So now we are getting A plus S. We are getting A plus S. So now it is the reverse of our actual rule, S plus A. It is reverse of our actual rule, S plus A. So it reduces to S. And once it is done, we'll pop the starting symbol of the grammar, pop S, and we'll pop the Z0. So here what we observe that as we are shifting the input on the stack, our string will be in a reverse order. Our string will be in the reverse order on the stack. Right? So that you can see here as a mirror image. So best way to solve this example is first you generate a leftmost derivation, top-down fashion, put the mirror, and you can generate a mirror image first. So this mirror image will clearly tell you that which reductions you have to apply. Otherwise, you will not get the correct result, right? First, you have to generate a top-down, leftmost derivation, top-down parsing, then create a mirror image of it. Just I have created a mirror image, as you can see here. So as you create a mirror image, you will know which reductions we have to apply. And then you will get the starting symbol of the grammar. So is this diagram clear? Is this clear what we are doing here? Yes, is it clear to other students? So basically what we have observed here that when we are pushing the symbol on the stack, right? So we require push and pop rules for the push down automata. So we are pushing A on the stack. At that time, the top of the stack is Z0. Second rule is we are pushing plus on the stack. At that time, top of the stack is S, capital S, right? Similarly, when you push A on the stack, the top of the stack is plus. So you can see we have various combinations of this top of the stack and the input symbol. We have various combinations of top of the stack and input symbol. So instead of writing every rule for push operation, we'll write one general rule. Q sigma x is equal to Q comma sigma x. So Q is the state, right? Because we don't want to write every combination. It will be infinite for a very large grammar. So we don't want to write every combination of push rules. So we are writing a general rule here. Q is any state. Input is small sigma. Top of the stack is capital X. So we are getting Q comma sigma X. So whatever the input symbol is there, whatever is the top of the stack, if the state is Q, we are getting Q comma sigma X. We are writing a push rule. So we'll write only one push rule with two variables. One variable for the input, another variable is for the top of the stack. And our state will be Q state always. Our state will be also Q. In top-down PDA also we have seen that we are able to generate a top-down PDA with three states only, right? Q0, Q1 and Q2. If you recall the last lecture, we are able to generate a top-down PDA with only three states, Q0, Q1 and Q2. Similarly over here, we'll generate this bottom-up NPDA with only three states, Q, Q1 and Q2. Okay, so now let us understand the other part of this. Let us have one more string, A plus A plus A. So first we are doing a leftmost derivation to identify the correct reduce moves. So leftmost derivation will give us S plus A. Then again leftmost S will give us S plus A, N plus A. And finally we are getting A plus A plus A. We have generated a mirror image of that, A plus A plus A in the bottom of fashion. Then A plus S. Then in the bottom of fashion we are getting A plus A. bottom to top, and last we are getting S. So if you observe this, you can find that the leftmost A reduces to capital S. As you can see here, the leftmost A reduces to capital S. Then the A plus S reduces to capital S. One reduction is here. This A reduces to capital S. Then A plus S reduces to capital S. And then last, A plus S reduces to capital S one more time. We have three reductions here. So now we'll do that reductions here. So first, Z0 is on the top of the stack. Input is A plus A plus A. So we'll push A on the stack. Now this A is the leftmost A. This A is the leftmost A. So we have to reduce this A to S. As you can see here in the mirror image, we are reducing A to S. Right? Because we are doing the same thing, leftmost derivation, but on the stack it is in a reverse order. So our string will be also in a reverse order. Our grammar rules will be also in a reverse order. So we are doing that reduction. We are reducing A to S. And we are not consuming any input symbol at that time. Now, what we are doing, we are pushing plus on the stack. So it is shift operation. So plus S Z0. Now further we'll push A on the stack, or we can say shift A on the stack. So we have A plus S Z0. As we are getting A plus S, this A plus S is a reverse order of our grammar production. So this A plus S reduces to S. That also you can see here in the mirror image. You can see here in the mirror image. So we are reducing to S, SZ0. Now after getting this S, we'll shift plus on the stack. So it is plus SZ0. Then we'll shift A on the stack. So A plus SZ0. It will reduce to S because it is in a reverse order on the stack. So we can apply the rule and we'll pop S and we'll pop Z0. So this is how we are able to perform the bottom-up parsing. We are able to reduce the input string into the starting symbol of the grammar. So now we have written a shift rule here that we have any state Q, our variable is sigma, small sigma, top of the stack is capital X. We are getting Q comma sigma X, Q comma sigma X. Now we have to write the reduce rules. We have written here the shift rule. It is a shift rule that for any variable and any X, we are writing Q comma sigma X, a shift rule, a general rule for all the shift operations. Now we'll write down the reduce rules. So you can see that we are doing this kind of reduction. A reduces to S. Another reduction is A plus S plus A reduces to S. S plus A reduces to S. Right? So we have two reductions possible. So these two reductions are based on two rules of the grammar. These two reductions are based on two rules of the grammar. So that is what we have to do. Right? That will assign rule number to each grammar production. And when we are doing the reduction, we are not consuming any input. And we are saying that we are consuming null. We are consuming null because we are not reading anything from the input. A reduces to S. Our state is Q. Our state is Q. We are not consuming anything when we are doing a reduction. Top of the stack is A. So we are doing a reduction. A reduces to S. So you can see here that this is how we are applying a reduction. S to A to S. We are applying reduction to rule number 2. It is a reduction rule. We are applying reduction to rule number 2. A to S. So state is Q. Always input is null because in reduction we are not consuming anything. A is on the top of the stack and that is reduces to capital S. So that is what we have done also in the previous example. You can see in the reduce step, A is on the top of the stack. We are not consuming anything from the input. Step number 2 in the table. You can see the step number 2 and 3 in the table. A is on the top of the stack. We are not consuming any input. It is as it is. And A reduces to S. A reduces to capital S. Step number 2 and 3. I hope you are getting this step 2 and 3. Right? So we are writing the reduce move for rule number 2. Now when we are writing a reduce move for rule number 1, it is interesting. Now we are writing a reduce move for rule number 1. S plus A, the reverse form on the stack. We are getting this S plus A in the reverse form on the stack. So now instead of 3 symbols on the stack, we are replacing it with 1 symbol. Instead of 3 symbols on the stack, A plus S, right? We are getting A plus S on the stack. You can see this step number 5 and 6 in the table. 1, 2, 3, 4, 5 and 6, reduce move. Step number 5 and 6. So A plus S, we have 3 symbols on the stack in the form A plus S. Order is A plus S. And that reduces to capital S. That reduces to capital S. So that is what we are doing here. That we are in a state Q. Input is null. We are not consuming anything. First, we are removing A from the stack. Because instead of 3 symbols, we have to put only 1 symbol on the stack. So we are removing A from the top of the stack. And it is Q 1.1 comma null. Q 1.1 comma null. So why we are writing 1.1? Because it is not the complete reduction. It is a one step of this reduction process. It is one step of the reduction process. So 1.1 means we have applied first step of the reduction for rule number 1. It is a 3-step process. Basically, for reduction of S plus A to S, it is a 3-step process. We have to first pop A, then we have to pop plus, and finally we are replacing S with S. So we are applying the first step of rule 1. So we are writing Q 1.1. So it is just like a mutual exclusion, that when you are in a stage Q 1.1, when you are in a state Q 1.1, you cannot apply any other rule because it is a part of the rule. Otherwise, what will happen? That if you are able to apply any another rule, then your PDA will be in a inconsistent state, right? Your PDA becomes inconsistent. So that's why we are writing Q 1.1. That means you have applied the step 1 of rule 1. So you can only proceed with that. You cannot go to any another state at that time. That's why it is 1.1 and null. So we are popping A. Then from Q 1.1, again we are not consuming anything during reduction. So it is null in the input. Plus is on the top of the stack. Q 1.2 null. So we have applied second step of rule 1. We have applied a second step of rule 1. Right? And we are just popping plus. We are just popping symbol plus from the stack. Third is Q 1.2. Input is null. Top of the stack is S. So if you compare with this previous one, you can see here, we are popping A first in step 5, then we'll pop plus, then S will be left on the stack. The capital S will be left on the stack. So we'll replace capital S with S, right, during this process. The top of the stack is S, Q, comma S. Or we can say we are not changing the top of the stack, right? We are popping A, we are popping plus, but we are keeping S as it is on the stack because both are S here. S reduces to S last. And now again our state will be a state Q. Our state will be a state Q. The reason is that now you are free to apply any another rule. You have applied the complete reduction. As you have applied the complete reduction, now you are free to apply any rule. So are these two clear? This is very important, that how we are writing the reduce rule. how we are writing this reduce rules. Right? If you don't understand, you cannot write for any new grammar. Shift rule is always common, right? Without worry about the grammar, you can write a general shift rule, Q sigma x, Q comma sigma x. It is common for all the examples. Only the reduce rule is the heart of this bottom-up NPDA, how we are writing the reduce rules. And that varies as per the grammar. You have to give the grammar rule numbers and then you have to do the reduction, right? Okay, so now what we have to do, we have to write down the rule for the acceptance, because still after, other than shift and reduce, we are doing two things. Last two steps, pop S and pop Z0. If you observe this table, last two steps are still left. We have written everything for shift and reduce. All the shift and reduce operations we have covered. Now we have to write down a rule for pop S and pop Z0. Pop S and pop Z0. So now for that we are writing these two rules. Our state is Q because we have applied either a shift or reduce. At the end we are getting the state Q. Q in the pop operation, we don't have any input. Pop S. So we'll just remove the top of the stack. Our state will be a Q1 state. It will be a Q1 state, Q1 null. We are popping S from the stack. So we are popping the starting symbol of the grammar. And last, S, it is our Q1 state, Q1 null Z0. For acceptance, Q2 null. We are popping Z0 also from the stack in the bottom of NPDA. Q1 null Z0, we are getting Q2 null. We are popping Z0 also from the stack. These are again fixed rules. So rules to accept are also fixed. They are always same for every grammar. Rules for shift is also fixed. It is applicable to all the grammars. Only change will be in the reduce rules. Only change will be in the reduce rules. So now, without doing all these examples, without doing this tracing for any string, we can write down the shift and reduce rules based on the grammar, right? So that you can see here, right? If I combine this all example, then based on the grammar also I can generate this four tables. The first is common, Q sigma x, it is Q sigma x, the shift rule, right? Q sigma x, it is the shift rule, which is common, we can write directly. Rules for acceptance, we can write directly, Q null S, Q1 null, Q1 null Z0, Q2 null. Now for reduction, we are using rule number 2 first. So Q null A, we are consuming null. A is on the top of the stack. So we are writing Q comma S. We are applying a reduction from A to S. We are applying reduction from A to capital S. Similarly, we are applying a reduction for the second rule. S gives S plus A. So in the reduction, it is reverse. A plus S reduces to S. Right? A plus S reduces to S. So from the state Q, input is null. Top of the stack is A. So we have to first pop A because we are replacing three symbols with one. So we are applying the first step of reduction. And rule number is 1. So Q 1.1 comma null. Then we are removing plus from the stack. So from Q 1.1, input is null. Plus on the top of the stack, it is Q 1.2 null. We are applying second step of the reduction. And then third, Q 1.2. Null, S on the top of the stack. So we are again going to state Q. So basically, we can say now we can apply any another rule, right? So this Q 1.1, 1.2, that is showing you the mutual exclusion, that once you are doing a part of the reduction, you cannot apply any another rule. When you are doing a part of any reduction, then you cannot apply any another rule. Once you complete the whole reduction, you are free to use shift and reduce rules. Is this slide clear? This is very important slide. Yes? Are you getting this flow? So I'm getting a response from 4 or 5 people: Priyank, Abhi, Janil, Munaf. What about others? Is this clear? Because you can see that it looks complex, but it is very easy to understand if you understand the flow. That why we are taking a reverse rule in the bottom up parsing. Our production rule will be in the reverse on the stack. Our input string, which is converted to starting symbol of the grammar, will be also in the reverse order on the stack when we are performing the shift operation. Is this clear? Okay, so we have one more example. Here we have 4 production rules. S gives S plus T, S gives T, T gives T into A, and T gives A. So we want to derive the string A plus A into A. So first we'll generate a top-down approach for our clarity. Otherwise you will find a problem at the time of reduction. So leftmost derivation we are doing S plus T. Then this is for our understanding purpose so that we cannot make any mistake in the actual example. Right? So this we have to do for our understanding purpose, top down to bottom up. So we'll find out all the reductions. Right? S gives S plus T, leftmost derivation. Then S reduces to S, from S we are deriving T. We are having T plus T. From T we'll derive A plus T, leftmost derivation. And then for this T, we have T into A. Again, it is a leftmost derivation. And last, we are getting A plus A into A in the top-down part. Now, when we generate a mirror image, you can see the leftmost A will Is this clear? Right? So if you look at this A into T, this A into T reduces to capital T. So you can see here, the leftmost A reduces to capital T, and then capital T reduces to capital S. And A into T together, A into T, it is in the reverse order on the stack. Right? So this A, which is the rightmost A, it will be as it is on the top of the stack. The rightmost A will be as it is on the top of the stack. The middle A reduces to T. The middle A reduces to capital T. And then A into T reduces to capital T. I hope you are getting this. Yes or no? Right? The leftmost A reduces to capital T, and then it is reduces to capital S. The rightmost A will be as it is. The middle A reduces to capital T, and A into T together will reduce this to capital T. A into T reduces to capital T. So I hope this is clear. Yes? So now let us see that how we are writing the shift reduce bottom up reduction. So we have a Z0, A plus A into A. So leftmost A will push shift on the stack. So we have A. Now as we know that leftmost A reduces to T. So we are applying reduction. A reduces to T. Then also this leftmost one reduces to S. So we'll apply one more reduction. SZ0. We are getting SZ0. Now we'll shift plus A, plus on the stack. So we have plus SZ0. We'll shift A on the stack. So A plus SZ0. Now this a middle A. This middle A, as you can see here, that middle A reduces to capital T. So we are doing a reduction. This middle A reduces to capital T. It reduces to capital T. Then we have shift operation. We'll shift multiplication on the stack. Again, we have A will shift, perform a shift operation. So A into T. Now as we are getting A into T, right? What we are doing, it is in a reverse order on the stack. So we are writing to T as per the reduction. So we have T plus SZ0. You can see that T plus S, again it is in a reverse order on the stack. This T plus S is in a reverse order on the stack. So we are writing SZ0. It is SZ0. And we'll pop S and we'll pop Z0. So now here you can see why we are telling it is a non-deterministic PDA. If by chance you don't do a proper reduction, right? If you don't do a reduction properly, that means after shifting plus A, first step, if you shift plus, because that is also a valid operation. Is it clear? You are shifting A on the stack, and then by mistake, if you shift plus on the stack, then what will happen? That branch of bottom-up parsing will crash because it is not the right path. You can perform a shift operation anytime. Here I am showing the correct path always. Here I am showing in this slide the correct path. Is it clear? I am not showing the entire path. I am just showing the correct path. So now what someone can do, someone can shift A on the stack and then immediately someone can shift plus on the stack. So if you will do that mistake, then what will happen? That path of your bottom-up PDA reduction process will crash. So it is not that always you will get the correct path. So this I am showing the correct valid path to get the acceptance, right? But there are many paths possible because you can apply shift operation at any place. So if you are applying a shift operation as at incorrect place, then definitely that path of bottom-up NPDA will crash. That means it will not reduce to the starting symbol of the grammar. It will not reduce to the starting symbol of the grammar, right? Okay, so now can anyone write in the chat window a shift rule? If it is clear now, can you write a shift rule for this NPDA, for this grammar? Now waiting for your response. A shift rule for this grammar, right? We have to write shift rule, reduce rule, and accept rule. Can anyone write shift rule for this? Yes or no? Like this, Q, then delta, then someone is written, good. So Q del X, right? It is a small delta, so it is Q del X. We are writing Q comma del X, okay. That is a shift rule, okay. Now we will write the accept rules. At least you people are getting the things, right? We have so many things to write, so you can write. Anyone else other than Priyank will write the accept rules. Rules for acceptance. That means pop S and pop Z0. That two rules. If someone can write. Is one such rule. So we require only this much of time. And these are the rules for acceptance. Q null S, it is Q1 null, and then Q1 null Z0, Q2 null, because we are popping the Z0 also. This is similar to what we have written previously. Q null S, Q1 null, Q1 null Z0, Q2 null. Right? Now the main thing will start. We have to write down the reduce rule. Okay, so we'll write the reduce rule for rule 4. Here it is the main thing. Reduce for rule 4. We'll write reduce for rule 4. So I think you know the things that in the reduction we are not using any input symbol. We have to give the rule number to all the rules. Yes, so we'll write. Because many students were writing, yes, we got the things. I know all the names, Munaf, Abhi, Jainil. Anyone else also? Yes, it is interesting. We will write the reduce rule. It is for rule number 4. I am looking for rule 4. Okay, here you have written for Q null A. It is Q comma T. Right. Vimal has given the correct rule. Q null A, Q comma T. It is for rule 4. Similarly, let us write for reduce for rule 2. Let us do the simple thing first. Reduce for rule 2. Let us write reduce for rule 2. So we all got the things. I understand. If you write the rules, I will understand that you are getting the things. I know that many people can write these rules, but you are not willing to write. Rahil can write, Zuzar can write, so many people can write. If you write, it will be good. If you make any mistake, I can tell that why it is wrong, right? Yes, so Munaf has written, good. Q null T, it is Q comma S, right? We are applying reduction, we'll pop T from the stack and then we'll push S on the stack instead of that. Definitely, it is correct. Now let us write for reduce for rule 3. Let's write a reduction for rule 3. Definitely we have three symbols here. It is in a reverse order on the stack. We have to do three reductions, and then you will get the non-terminal T. So let us see who is writing a reduce for rule 3. Yes, reduce for rule 3. Yes, if someone can write. Yes, Neerav, good. Q null A. Only rule number should be 3. That is the only thing, because we are giving a third number, right? It is not rule number 1. So otherwise it is correct. Q null A. The input is null, A is on the top of the stack, so it is Q 3.1 null. It is Q 3.1 null. We are applying first step of rule number 3, right? So that rule number is very important. You cannot write 1.1. That is the only thing. Otherwise, it is completely correct. Then Q 3.1 null star. So you are removing star from the stack. So it is Q 3.2 null. And then Q 3.2 null T, the last part. Again, we are getting QT, Q comma T, right? Is Nirav clear? You have to just write a rule number as 3, 3.1, 3.2, because we are applying to 3. Okay, now the last one. Right? Otherwise, it is completely correct. Reduce rule for 1. Now, we'll write a reduce rule for rule number 1. It is almost identical to but rule number will be 1. No, there will be a lot of change. Yes, sir, there is one query. Yes. Q 3.2, then null and T, then it is Q comma T. It will be T definitely, because T into A reduces to T. Q T into A reduces to T. So definitely the leftmost non-terminal will come, because we are doing a reduction. So T into A in a reverse form reduces to capital T in rule 3. It will be definitely Q comma capital T in rule 3. Right? So only what Nirav has written, it should be only rule number 3 instead of 1. 3.1 and 3.2. Right? I hope Priyank it is clear. Right? So you cannot write T to S. Q 3.2. Okay. I hope it is clear. Now let us write reduce rule for 1, because we are reducing the right hand side with the left hand side non-terminal. So that will come into picture. So we have to write for rule 1. Right? Once you write for rule 1, we can see the complete thing and we can proceed. So here we have a shift rule, we have a accept rule. Here we have a rule for reductions, as you can see here, and this is the last one. Right? Here you can see directly. Let us save some time. So Q null T, it is Q 1.1 null. We are removing T because we are removing the symbols from the stack in a reverse order. So capital T will be removed first. Then we are removing plus. So Q 1.1 null and plus. So Q 1.2 null. And last, Q 1.2 null capital S. That will give us Q comma capital S. So you can see we have a reduction rule for all the 4 grammar rules. I hope it is clear. There is no doubt in this. Yes? Is this clear? Okay, so similar to that, we can write for this new example. If you have any doubt, you can ask. Otherwise, it is straightforward. Right? Shift rule is as it is. It is a new grammar. S gives S within bracket S and S gives null. S gives S within bracket S and S gives null. So shift and accept rules are as it is. Only thing is you have to understand reduce rule. It is null to S, right? It should be rule to reduce null to S. So Q input is null, top of the stack is null, will reduce to Q comma S. Right, here it is. Reduce rule for the second. Q input is null, top of the stack is null. We have Q comma S. We have a Q comma S. A green color you can see. The second is we have 4 symbols here in the rule 1. So Q, null, and closing bracket because we are getting in a reverse order. We are getting these rules in a reverse order. So Q, null, closing bracket, Q 1.1 null. Then Q 1.1 null, capital S, we are getting Q 1.2 null. Q 1.2 null. Then Q 1.2 null, opening bracket. So we are getting Q 1.3 null. Q 1.3 null. And last Q 1.3 null, capital S, we are getting Q comma S. So it is a 4-step process, 1.1, 1.2, 1.3, and finally the last step of the rule. Is this clear? So you can see that here we are not doing that derivation and all that. We are not taking any string, but we are directly writing the rules based on the grammar. But now I think it is clear that why we are writing rules like this. Right? Shift, accept, always common, and reduce rule for null to S. And another rule is S within bracket S to S. Is this clear? Any query in this example? Yes, can we proceed? Yes, how we have written the rules. It is clear, I think. So here you can see we have taken one example from that. We want to derive this opening bracket and closing bracket. You can see here from this S within bracket S, and for S we'll put null, leftmost derivation. Then within bracket S is left. Again we'll put null. So we are getting opening and closing bracket. Now in the stack, it is in a reverse order. So you can see what we are getting: null, then opening bracket, then null, and then closing bracket. So this closing bracket will be on the top of the stack. And don't confuse here. This looks very complicated, but it is very simple. The closing bracket will be on the top of the stack. The opening bracket will be inside the stack. And this null is playing a pivotal role. You can see I am writing null also. I am writing null also. Right? So you can see that null reduces to capital S. So first, in the first step, what we have to do? We have to consider null on the stack, and that null reduces to capital S. So you can see here that without shifting anything, without shifting anything, we are reducing null to S first. We are reducing null to S first. So we are getting S in that way. Then we'll shift the opening bracket on the stack. So we are getting opening bracket. Now again, what we require? We require this null. We require this null. So again, we have a reduce. And we are introducing another S. S closing bracket S. Sorry, S opening bracket S Z0. S opening bracket S Z0. Then we'll shift closing bracket. As we are getting this, we are applying the first reduction directly. Rule as per the reduction as per rule 1. We are getting capital S. We'll pop S and we'll pop Z0. Is this clear? Right? So you have to consider this example very seriously. Right? Otherwise you will feel that what we are getting everything on the stack which looks very unusual. But you have to understand this thing, that we are shifting the string on the stack in a reverse order. So everything you will see in a reverse order on the stack. And this flow is very important, that if the question is reduce the given string into S, then you should generate this kind of table. Right? Reduce the given string into starting symbol S, then you have to show all these steps. So you should know that when null reduces to capital S. If you know that when null reduces to capital S, then and then you can do the proper reductions. I hope this is clear. Is this clear? Can we proceed? Now no one is writing yes. So far I found some at least yes, but in this example, no one is writing. Okay. Okay, so I got at least some yes. A few, very few. So we want to derive this string, right? So we are doing a bottom-up approach. So from S, we are writing S within bracket S. So that is what here it is, that we have a rule, null reduces to S. We have to, when you are doing a leftmost derivation, you can see that S is replaced with null. S is replaced with null. So in the reduction, null should reduce to S. Right? In the derivation, we are replacing S with null. In the leftmost derivation, in top-down parsing, we are replacing S with null. So in the reverse scenario, bottom-up approach, null will reduce into capital S. Null will reduce into a capital S. So you can see that when you generate this mirror image, you can see the first step is we have to consume null, because null is on the top of the stack. Null is on the top of the stack and we have to do that reduction to get the capital S. The first step is reduction. We will not consume any input. We will not will not shift opening bracket on the stack, but will reduce null to S. We'll consume null from the stack. So we'll reduce null to S and we'll introduce capital S. Because as you can see in the mirror image, null reduces to capital S. Null reduces to capital S. Then we'll shift opening bracket on the stack. Again, you can see that after opening bracket, we require what? Capital S. We require capital S in the mirror image. Right? So now to achieve that goal, we have to again do a reduction of null to capital S. We are doing that. We are reducing null to capital S. So we are getting S opening bracket S Z0 on the stack. S opening bracket S Z0 on the stack. Now we'll shift closing bracket on the stack. As we are getting closing bracket S opening bracket S on the stack, we'll apply the step 1 of the reduction. we'll apply step 1 of the reduction, and we are getting SZ0. Right? Okay, so definitely this needs a practice. Once you practice, you will understand these things more. So now let me explain some small thing which is left. Okay. Let us understand complement of a CFL is not a CFL. We'll prove this theory by a contradiction. Let us assume that complement of a CFL is a CFL. We'll assume that complement of a CFL is a CFL. So we are taking one language, a raised to I, b raised to j, c raised to k, where I and j are equal. We have already written a context-free grammar for this language in the previous lectures. So I and j are equal, so definitely we can write a CFG for that. We'll push a, when b will come, we'll pop a, so a and b will cancel out, and we have any number of c independently. So a complement of CFL is a CFL as per our assumption. So definitely L1 dash is a CFL as per assumption. Similarly, we have another language L2 where j is equal to k. So definitely L2 is a CFL. So complement of CFL is a CFL as per assumption. So L2 dash is also a CFL. Now also we have seen in the previous lecture that the union of two CFL is also a CFL. Right? We are solving the examples like this: I equal to j or I equal to k, if you recall the chapter 6. Right? So union operation we have seen that it is permitted in CFL. So union of two CFL is a CFL. So L1 dash union L2 dash is also a CFL. L1 dash union L2 dash is also a CFL. Now, complement of a CFL is a CFL. So we are writing like this, that complement of L1 dash union L2 dash, complement of L1 dash union L2 dash is also a CFL, because we are assuming this, that complement of a CFL is a CFL. Now, as per De Morgan's law, L1 intersection L2, we are getting L1 intersection L2. Now, L1 intersection L2 means what? That a raised to I, b raised to j, c raised to k, I equal to j and j equal to k. We are looking for this kind of grammar for this kind of language. A raised to I, b raised to j, c raised to k, I equal to j and j equal to k. So now you cannot create a push down automata which will compare equality of A and B, and at the same time it will compare equality of B and C. We cannot do these two comparisons with one stack. We cannot do these two comparisons with one stack, that I and j are also equal and j and k are also equal. That is not possible. It is not a CFL, right? Because we are always comparing one thing in the context-free language. So I equal to j and j equal to k. So you cannot compare B and A and B and C both. Because if you push A, when B will come, you will cancel B with A. So you can do one comparison A and B. Or you can compare B and C. You will push B. When C will come, you will cancel B. So you can either compare A and B, or you can compare B and C. But you cannot do both with one PDA, with one stack. So our assumption that complement of a CFL is a CFL is not correct. Because if it is a CFL, then we are able to write a CFG for this language, L1 intersection L2. Is it clear? We are able to write a CFL for this, for CFG for this CFL. So complement of a CFL is not a CFL. So I hope it is clear. Very simple thing, right? Just we are focusing on this one criteria, that we can create a CFG for this language L1. We can create a CFG for L2, but we are assuming that complement of L1 and L2 are CFL. So we are finding L1 dash union L2 dash, because union of two CFL is also a CFL. And again, complement of this will give us L1 intersection L2. Complement of this will give us L1 intersection L2, which is not a CFL. Which is not a CFL. So thank you. all. So I am ending this session now. Thank you.